All right, so in this video, we're going to be going over sections 4.8 through 4.10, and this is going to cover trig, exponential, and inverse derivatives. All right, so to start this off, we got to go over some first basic things. We're going to have to know that the derivative of sine of x is just going to be cosine of x. And then our derivative cosine of x is going to be equal to negative sine of x. And then the derivative of tangent of x is going to be equal to secant squared x. Then the derivative of cotangent of x is going to be equal to negative cosecant squared x. And then derivative of secant x is just going to be secant x times tangent of x. And then finally, our derivative nicer, derivative of cosecant of x is just going to be equal to negative cosecant cosecant x times tangent x. Now, to start off with trying to figure this out, let's do some trigonometry stuff first. So let's say example set. Let's say we have a function f of x, and that's going to be equal to secant 3x squared minus 1, right? So what we need to remember here that is we see the composition of two functions here, right? So what we need to remember is our chain rule. And our chain rule states it's the derivative of inside of g of x times g prime of x, right? So what we have to do here is find the derivatives of each one of these respectively, right? Take a look first in our f prime function, right? Well, let's make this a little easier. Let's say that f of x is going to be secant x, and our g of x is going to be our 3x squared minus 1, right? Let's think about it. If we replace, like, let's say we have the secant function, right? And we replace the x value with whatever our g of x is, that's the same as f of g of x. And that's essentially what we want, right? And then we can take the derivative of each one of these respectively. So f prime of secant, right? What was the derivative of secant? We can come back up here and look. It was secant x times tangent x. So, but we have to remember, we have to put in our g of x, right? So this is going to give us secant 3x squared minus 1 times tangent of 3x squared minus 1. Another parentheses there. And then the last one just says our derivative of g of x. And we can see here, get rid of that negative 1 because it's a constant. This is just going to become multiplied by 6x. And that is going to be our derivative for that function. Let's go over another one. Say we want the derivative of, make this h of x, of sine squared x, right? So similarly, how I think about it is we want to break this up into an f of x and a g of x. So we can think about like a composition. Let's say our f of x is going to be squared function, and our g of x is going to be our sine x function. Because if we think about it, if we put in our g of x, right, our sine, into our x squared, if we combine those together, we're going to end up getting sine squared. And that's exactly what we're looking for. Then we can take their individual derivatives, this one being 2x, and g prime of x. You can look up here, but that's going to be cosine of x. Now we can apply our chain rule, right? And what that's going to give us is that we want our 2x, and then we put in our sine. So this is going to be 2 sine x times g prime cosine of x. So we're just left with 2 sine x cosine x. Now, get into another one that's very similar, but a little bit different. So let's say h of x is going to be x squared, not sine squared, but sine x squared, right? So it's a little different. Our f of x is now going to be sine x, and our g of x is going to be x squared. Because if you think, if we have our sine function here, our base sine function, and we replace the x here with our g of x, we're going to get sine x squared. But everything still functions the same way here. We're going to take the derivative of f of x, which is just going to give us cosine of x, derivative of g of x, which is going to give us 2x, same like before. And then we apply our chain rule, and this is going to give us, see cosine here, cosine here, let's look here. This is going to give us 2x cosine x squared. There we go. Now, do a little bit of a different one, a little bit more complicated. Let's say we want to find the derivative of h of x when it's cosine squared x plus 3 tangent x, right? So first things first, you got to break this down, right? Because we can already tell what the derivative of 3 tangent x is, right? We can just look up here, check. Derivative of tangent is just going to be secant squared x. And times 3, we know that this is just going to be 3 secant squared x. This one, we now get to break it down, bring it over here. This here. We now can say, I want an f of x and I want a g of x. Because we know that this is the composition of two different functions, right? And so we can say that our f of x is x squared and our g of x is cosine x. Because if we put our, our x squared here and we replace our x with the g of x, we get cosine squared. And that's what we're looking for. And then just like how we did before, take the derivatives of each side. We look, the derivative of cosine is negative sine x. Then we apply our chain rule, and then we get negative 2 cosine x sine x. And then all we have to do is add that on to our derivative of 3 tangent, and then here, I'll bring it over here. We get the derivative of h of x is going to be negative 2 cosine x sine x plus 3 secant squared x. Boom. And that covers everything you need to know about trig derivatives. So the next thing that we can go over now is exponential and logarithm rules. Let's write this here. Exponential and log rules. So this is kind of a good bit to write down, but this is here. So the first thing we can go over here is that e to the x times e to the y is just equal to e to the x plus y, right? And then if you have e to the x raised to the y, that's going to be equal to e to the xy. And then if you have ln of x times y, this is going to be equal to ln of x plus ln of y. And then if you have, say, ln of x over y, this is just going to be equivalent to ln of x minus ln of y. Then, sorry, this is a lot of rules for exponentials and logarithms. If you have ln of a raised to the k, this is going to be equivalent to k times the ln of a. And then you have some inverse rules where if you have the ln of e to the x, this is just going to be equal to x. And then correspondingly, e to the ln of x is going to be equal to x. And then if you have log base a to the x, this is just going to be equal to x. And then if you have a to the log base a of x, this is just going to be equal to x. And then lastly, only two more things we need to go over for this, at least for our rules. The derivative of e to the x, it's a little clearer, of e to the x is just going to be e to the x itself. And then the derivative of ln of x is going to be equal to 1 over x. Now, with all those rules, we'll be able to now solve some problems with this. So, for our first examples here, say example set 2, we have h of x is going to be equal to x squared e to the x, right? So just how we did before, I like to break this down, right? But we can see that this is a multiplication of two things, so you know that we're going to be using the product rule this time. But so let's say that f of x is going to be equal to x squared, g prime, g of x is going to be equal to e to the x, f prime of x is going to be equal to 2x, g prime of x is going to be equal to e to the x, as we just learned before. And then we apply product rule, which I can write that down again here. Product rule states that f prime of x times g of x plus f of x times g prime of x. So we take our f prime, that's 2x, then our g, that's e to the x, plus a regular f function, x squared, times g prime, e to the x, and then we could even take out an x and get e to the x times 2x plus x squared. And that gives us our derivative. So I'll take another one. Let's say we do h of x is equal to e to the 2x squared plus 1. We can see that this is a composition of two functions, right? We can say that our f of x is e to the x, and our g to the x is 2x squared plus 1. Because if we have our base function e to the x and we replace x with our g of x, we get our same exact function we have here. Now we can take our derivatives of each part. So derivative of f of x is e to the x. The derivative of g to the x, 4x, not plus 1, just 4x. There we go. And now we can apply our chain rule, which, if you remember, our chain rule is f prime g of x is g. Oh, break it down here. So we have our f prime. Prime is going to be e to the x, and then we have our g is just going to be 2x squared plus 1. Now we need to multiply this by our g prime, which is just 4x. Oh, now once we do that, we can just say that the derivative of this is just 4x e to the 2x squared plus 1. Now we can move on to the next thing. Let's say, let's say we want to find the derivative of h of x when it's e cosine 4x. So in order to do this, we still need to break it up. into the composition of two functions. So we can say that, like before, h of x is e to the x, and g of x is going to be equal to cosine 4x, right? And so we take the derivative of this side, going to be e to the x. And then we notice here that this one, cosine 4x, is also a composition of another two functions. So then what I like to do is try not to get confused with me here, but I break this down again into f of x and g of x. So f of x becomes cosine x, g of x becomes 4x, right? Because we replace our x value in the cosine with 4x, we end up getting cosine 4x again. And then you can individually take their derivatives, negative sine x, and then 4. You can then say that our actual derivative of g to the x, let me put a line here to make it a little bit more clear. Our derivative that we've been looking for this whole time is actually going to be, let's see, let's apply it, should be negative 4 sine 4x. Fix this 4x. Now we can actually head in and use our f prime with what we had here, and then apply what's called the chain rule. Remember, our chain rule states that f prime of g to the x is g prime. Now we can do that. We know that our f prime is e to the x, so we have e, and then our g, just our g, is going to be cosine 4x, and then put parentheses here for now, and then times our g prime of x, which is negative 4 sine 4x, and then boom, that is our h prime. Now, all that we have left to cover now is inverse functions. There's not really a whole lot you need to know about that other than just a couple rules on what to do if you see an inverse function. So no example problems for this, but just a couple rules. So first thing is that y is going to be equal to, not the derivative, it's going to be equal to the inverse of f of x, meaning that f of y is going to be equal to x. And then if you want to find the derivative of the inverse function, you have to remember that it's just going to be equal to 1 over f prime of the inverse. Low-key kind of a mouthful to think about, but just to do it, think you want to take the 1 over the derivative of the inverse of that. And then you have a couple more rules for the inverse trig functions. Like d over dx is going for sine, inverse of sine, is going to be equal to 1 over root 1 minus x squared. And then the derivative of the inverse of cosine is going to be equal to negative 1 over root 1 minus x squared. And then the inverse for tan, the derivative of that, is going to be equal to 1 over 1 plus squared. And with that, that's going to cover everything that we need to know for sections, what we go over here, sections 4.8 to 4.10, trig, exponential, and inverse derivatives. And as a brief little overview, we learned about all of our base trig derivatives, what those were, and able to do a little bit of derivative work with compositions of those, being able to manipulate that. And then we also learned about a couple rules for exponentials and log rules, and a couple inverses, because we know that our exponential function and our ln function are inverses of each other. We were able to figure out those and then get the derivatives of ln of e to the x with each one of those respectively. We did a couple problems with those. And then finally, we also went over a couple rules when it comes to our derivatives for inverse functions. And with that, it covers everything